So this morning we heard from Mari about the PAWR testbeds and the powder testbed, and I'm delighted to welcome David Johnson from the University of Utah. So David is a researcher and software engineer at the Flux Research Group and is responsible for a lot of the good work that's happening within the powder testbed. Welcome.
Thank you, Paul. And before I get going, thank you. Before I get going and forget to thank everybody in the room, especially thank you to the SRS guys for all of your good work at developing such a stable and performant stack that we've been able to use in so many cases. All right, let's see if I've got the right thing here. All right. So I have lots of material to cover. I've talked to a lot of you. I know there's different amounts of interest in different features of the powder platform, and I'm also trying to talk about how we're evolving into the future. So there's a lot of reference material in this deck. The slides will be open, offline for you to kind of catch up on our status as to what we have deployed, what we have operational. But speaking being operational, we've been operational now for a number of years. We've supported 5G, LTE, O-RAN, mobility experiments, massive MIMO, all kinds of cloud stuff, and really a wide variety of bring your own device experimentation, from custom fabbed antennas, all the way to ORUs and things like that. We're always trying to extend the core platform. We're adding new devices. We're adding some of the Benetel ORUs that are compatible with srsRAN. We're taking lessons learned from our Spectrum adventures over the years and building platforms to build modular RF front-end systems. We're adopting contributions from the open source community as new features are released in new stacks. We're making those available to our users and testing them. There's also been something that we found really valuable to provide to the community, which is our end-to-end use cases. I'll talk about the details of those, but one of them, was really central around srsRAN. We did an early E2 enabled fork of that to do some RAN slicing, and we shared that with the community, and it's been really well received. We've done a number of trainings with it. We've supported students and organizations to use it to bootstrap some of their efforts. So that's been really cool. We're looking to do more of those end-to-end use cases and make them available to the community. Some of the main challenges we see in evolving powder into the future is dealing with Spectrum. So we're embedded in Salt Lake City. Unfortunately, we don't have PAL access to CBRS. So Spectrum has always been a challenge for us. So we're participating in the National Science Foundation's NRDZ program, and we're building a prototype ZMS, but it's real software backed by a digital Spectrum twin. So I'll talk a little bit about that. This ecosystem is diverse, complex. There's millions of miles of middleware here and stacks to enable people to use. And lots of people, when they do experimentation in this, want to put their own spin on it and their own stamp on it. So we're trying to provide an automated framework to help accommodate those things. We'll provide a library of pieces that can be composed together, and we'll try to provide some automation glue, and people can add their special sauce. But like I said, that's a huge challenge for us. So we have some mechanism, and I'll talk a little bit about that. This is a classic three-legged stool feature. If you know my colleague Cobus Vandemerver, the PI for the Powder project, you know of his rule of threes. So this is his current rule of three slide, and it really nicely illustrates the different pieces that are tied into the Powder ecosystem. And these are the things that I just mentioned that we're kind of working on. So we have the operational Powder platform at the base. It's very useful and it's a key enabler for both our research into radio dynamic zones, where we see a lot of potential for spectrum sharing, as well as our automated test framework that is key to things that we do under the auspices of being an OTIC. I'll be brief here. I want to get to the status of what we have and talk about some of the new things. But really, Powder, as Mari said, Powder is very programmable. Excuse me. It's end-to-end software defined. You can load whatever you want on the building blocks. The hardware is yours. You have full remote access. You've got power control, serial consoles where you need them. And our deployments around campus and in the different data centers where our equipment is are all extensible to bring your own device kinds of models. This is kind of a nice overview map of where Powder is right now. I reflected to myself that this map is getting a little bit crowded, so it's harder to make out the different colors. But these are kind of summaries of the radio cabinets we have deployed on campus. Solid black lines are fiber. There's a downtown data center on that side. There are 2 data centers, but they're hiding in the in the density of the map here on campus. I guess I would say that the dark blue blobs are our rooftop base stations. The light blue blobs are human height radio cabinets on the sides of buildings. There's a new green area that's our dense deployment, and I'll talk a little bit more about that later. And the red dots are our lamppost style cabinets and enclosures. All of these have software-defined radios. They have COTS devices. We're adding COTS RUs, as I mentioned. They have Quectel RM520s, most of them. And then over on the right side, the inset figure just shows some of the bus routes. So the university operates shuttle services for visitors and students, and we have mobile devices or mobile radios inside of those, and you can see how they trace around the fixed wireless deployments on campus. These are all remotely accessible as well, even the buses. So we have about 10 rooftop base stations, I guess 9 right now. One of the buildings was a medical school residential building that was recently demolished or is about to be demolished. So we're in process of replacing that. We have about 25 shuttles, 10 fixed endpoints. We have some portable endpoints as well, but really these follow a similar kind of form factor. Powder is federated with Cloud Lab and Emulab. These are other test beds that we've built. So Powder users have access to hundreds of powerful servers. Many of them are FlexRAN enabled. Many of them are connected to Syncy enabled, PTP enabled networks with Grandmasters. So you can do all the kinds of ORAN experiments you would like. And they have accelerators. One thing, so I give this talk a little bit differently than Cobus. I wanted in this case to talk about how people use Powder. Sometimes it's a brute force reveal of all the resources that we have, and people don't really know what it means. So just really quickly, don't necessarily try to understand that complicated figure. But what we do is similar to a cloud model. When people come to Powder and try to use Powder, they create a project. A project like in a cloud would be a unit of user teaming. That's how you allocate resources. You get your isolated environments within a project. We provide a library of what we call profiles. These are descriptions of the resources that you want, how you want them configured, the software they should run, runtime customization scripts. And once you've picked a profile or created a custom one, if you need to, if you can't use one of our base profiles, or if you fork it, then you can create your experiment. And this gives you a dedicated allocation of resources. You can use Powder through a GUI API. We have a very powerful reservation system that's pretty flexible across node types and specific nodes. We provide a bunch of data collection and RF characterization tooling to try to help people use Powder more effectively. And the goal with the profile mechanism is that it's this repository of building blocks that people can use to quickly stand up complicated end-to-end scenarios. This is another view on that world. These are the kind of different stacks that you could stand up if you wanted to. So we typically provide bare metal Linux or Linux in a VM to people. And we have a bunch of profiles that stand up things. There's a big ORAN profile that stands up the open source RICs in different versions and different configurations. These profiles are parameterized. So if you want your Kubernetes to change a little bit, you can do that. This is what our web interface looks like. On the figure on the left is just showing what a user would look like when they click to run our ORAN profile. So there's some documentation. It's actually a Git repository. So it's versioned. You can instantiate from a branch or a commit. Kind of cool. There's a long laundry list on the right side of all of the parameters that are inherited from the Kubernetes profile. So it's kind of the foundation for doing business in this space. So complicated, but powerful. This is a demo that we've done in collaboration with Spectrum Exchange, Xylenium Research. Mari mentioned this in her slides. I have the same slide in my deck, so she saved me a bunch of time there. But this is what experiments look like, doing ORAN looks like. On the left, I have an ORAN node running from our ORAN profile. I think this one probably has the near real-time RIC, and it has a custom X app that we wrote long ago. And the experiment on the right has 3 B210s connected to NUCs. 2 of them are UEs, and 1 of them is a node B. And so we did some spectrum sharing demos in collaboration with Spectrum Exchange. Briefly, I'm not going to go through the details again, but these next slides list the equipment that's in our radio cabinets, the software-defined radios, the compute in the cabinets, COTS UEs. And down here, this is what the fixed endpoints look like. So this is a climate-controlled, multi-layer chassis. There's compute on the top. There's SDRs on the bottom that you can't see, and then there's antennas that surround it. The mobile endpoints look much the same. They're constructed in much the same way that the fixed endpoints are, and similar kinds of equipment, slightly different. The rooftop nodes, the cabinets are a little bit bigger. They actually have real racks in them, so they're a little bit more expansible to bring your own device. And we have had people add stuff to these cabinets. These are fiber backhauled, whereas the wireless backhauled. A portable endpoint looks much the same as the others. There's just a little bit more space in it. We also support massive MIMO experimentation, and we have a number of the Skylark Pharos arrays on campus, 3 of them on some of our rooftops, and we have clients that can use them, and people have done some interesting massive MIMO research using this. And we're supported here by Rice University and the Renew project developing software and helping to support this deployment. The dense nodes are a more recent deployment. This is a densified deployment that's cited in particular along one of the shuttle routes. So you've seen my colleague, Dustin Moss. Dustin, can you wave your hand? Dustin's running a demo out in the hall that's running srsRAN 5G on base stations on these dense endpoints. And then there are COTS UEs that are attaching and detaching to those base stations as the shuttles trace through the network. These are interesting because they have in an early version of our CBRS RF front-end built on our modular RF front-end platform. And I think this is a 4-watt board. Yes. So that's obviously pretty cool to have, but we believe that this is key to evolving powder to target different spectrum in a much more agile way than fabbing a complete RF front end to target a particular band, which is what we had to do originally. Mari mentioned that we did have access to, prime commercial grade spectrum at one point, but the carrier kind of ate the band. Of course, that was bound to happen someday. Unfortunately, it happened just as we had our board deployed. So that was unfortunate timing, but we've learned our lesson. Now we have a better platform to build on in the future. I didn't really talk about time. I guess I talked a little bit about PTP and Grandmasters and that's available at our fiber connected nodes. We also have the White Rabbit synchronization system to provide sub-nanosecond accuracy directly to our radios. This is just another slide that kind of shows the demo that Dustin is running out in the hallway. So I'm going to let him talk about the details of that and how that is. But we are hoping to deploy those Benetel 550s as soon as we can and get them linked into the version of that demo. These are just some photos that show some of just a couple of the bring your own device cases that people have stood up. Oftentimes they do them on the rooftop deployments. As Mari mentioned, we have a program experimental license from the SEC. We're an innovation zone that allows us to operate in some of these frequencies, and we're kind of seeing if we can expand some of these things. There's a ton of people who have worked really hard over the years to do this. It's quite hard to have all this equipment deployed, fabricating power boards, RF front ends. There's a lot of challenges. So shout out to all these guys. And we're grateful for the public-private partnership. I think, in my view, that's been a great success and a key enabler for us. So I know that there are a bunch of people in the room and just want to thank you for your support. I want, again, another feature of Dustin's demo is that he's talking about the way that when you use powder, you can sort of seamlessly transition all the way from simulation up at the top, all the way down to outdoor OTA. And you can go through a phased approach of exposing your experiment more gradually to increased levels of realism. One thing that's not in the blue boxes is our RF attenuator matrix. So we have programmable attenuation control. So when I stood up my end-to-end ORAN use case, I stop at the scheduler. I'm not don't ask me any hard RF questions. I'll fail them all. Ask Dustin those. But anyway, I followed this exact same approach. Of course, I simulated. I went to the matrix. I gradually added more and more amounts of control loops. This is that use case that we stood up. We called it srsRAN. We started doing this in 2019, and this was back in the days before deploying the OSC near real-time RIC actually required Kubernetes. So those were kind of good days in that sense. But this is, again, this was a RAN slicing and a RAN sharing use case eventually. A lot of the ORAN infrastructure didn't exist at the time, so we had to build a lot. But we found that, again, that was an enabler for the academic community. At the same time, I'm more than happy to stop maintaining that fork now, and thankful that Justin has done all the work now, and the team. This is a slide Mari showed you. I noticed it says OAI in there. There was a whole bunch of srsRAN also on that slide, and our collaboration with them has been mostly focused on building these ORAN building blocks with srsRAN. And we're eager to evolve this use case, I think, to newer srsRAN. I think there's pretty direct mappings between the RC service model and possibly with some support from the CCC service model. So that'll be fun. This is an interesting BYOD use case just because of the complexity that it required to assemble. So as an OTIC, we've been supporting PlugFest for several years now, and this was a really large energy efficiency, energy savings use case. I think Radisys at that time provided a DU and a CU running on a Wind River cloud, and Keysight provided, testing equipment to bracket the thing, and a power analyzer that's worth more than my cars, and all that stuff. But that was a really important use case to be demoed in a PlugFest, and at the time there was an awful lot of interest. There still is a lot of interest in energy efficiency and energy savings in the RAN. Okay. Now I'm going to talk about how we're trying to deal really actively with spectrum. So the National Science Foundation has a concept called the National Radio Dynamic Zone. And the idea here is that it's the exact opposite of a national radio quiet zone, where you think about a radio astronomy telescope. It's paramount that you not interfere with a global network of time-aligned radio telescopes that are taking pictures of black holes and doing awesome things, right? But at the same time, there are those of us who want to transmit, and we need to transmit safely and coexist in parallel with other users in a geographic area. So we are prototyping the system. We call it Powder RDZ. We're building a zone management system in the purple box with an orchestrator with services to facilitate that sharing of spectrum. We're taking a fairly greenfield approach from a software engineering standpoint. It's cloud native. We're developing our own APIs, and we're inspired by efforts that have gone before and efforts that coexist. But by taking a more greenfield approach to the API design, this allows us to think maybe a little bit more broadly than some of the existing APIs about the spectrum sharing use cases that we can support, even thinking about NTN cases. Of course, the way that we're building Powder RDZ, it's not tightly coupled to Powder. Powder is a key enabler, but Powder implements the APIs that we've designed for the RDZ and not the other way around. At the same time, if I didn't have Powder in my back pocket, I would not have been able to prototype the RDZ ZMS as quickly as I did. Just the sheer flexibility, the access to radios, the access to the infrastructure was really important. And eventually the automation piece will be important too. When you think of supporting users with experiments that use shared spectrum, we may have, an hour worth of spectrum from somebody, I hope, sometime in the future. And we schedule that for an hour block of experiment that needs to be fully automated. Results need to be fully captured. I'll talk a little bit about how we do that when I get to the automation section. But really briefly, our architecture consists of 3 different logical interfaces as part of the zone abstraction layer. There's a spectrum provider interface that allows parties who want to provide spectrum to the zone and delegate the management of that spectrum to the zone to manage, run propagation simulations, deconflict parallel use, that kind of thing. There's an interface for those who implement the zone abstraction layer to implement a monitoring interface to provide actual samples from radios that they may have operating under their control. And of course, the zone would have its own monitors to validate transmissions, make sure that sharing is happening. If interference reports come in, they can be automatically analyzed for veracity based on the other monitors that the zone has available. And of course, most importantly, from my perspective, is the consumption interface. Since I don't have spectrum, I want to consume it. Or I don't have as much spectrum, I want to consume it. This would allow me as a user to do similarly to as what a CBSD currently does to a SAS, just hopefully in a little bit more of a flexible way with additional constraints that allow tight sharing and safe sharing. This approach is really augmented by a lot of cool work that's going on at Georgia Tech, Serhat Tadiq and Greg Durgan, and they've built a TIREM-based propagation simulation. And this is kind of the core of what's going to allow us to deconflict multi-party use in the same bands. So the output of these simulations is primarily maps and probability of interference and things like that. It is TIREM-based, but then Serhat also developed a cool machine learning model that relies heavily on a very detailed CBRS data set that was collected on powder, and that corrects the predictions or enhances the predictions, as he would say. So we're actually tying this into our zone management system right now. I just did the first round of parallelization a couple of weeks ago. And that's important because a simulation like this takes many hours to run on a single machine. We need to get it down to, say, like 5 seconds at half meter granularity across a 4K by 4K area for this to be meaningful, to really facilitate true multi-party coexistence at scale. Okay. So I mentioned that we're NOTIC. We've been supporting PlugFest for a long time. And key to our approach early on in that process, we kind of saw how, and you know, I don't want to be pejorative to the testing that happens at ORAN PlugFests. Early PlugFests are always about manual plugging. There's always a lot of that. You know, it's impossible to get away from. But thanks to the open standards and open interfaces, I think we really have an opportunity to provide, you know, continuous testing that doesn't just sit on the equipment forever. There's testing and automation and automatic orchestration that stands up these environments end to end, runs the test, triggers whatever test suite we have, and then tears them down. This allows for that time shared and space sharing that's so important to us. So we wanted to make, when we built this framework and tried to conceptualize this idea, we wanted to enable the universe of tools that already exist. And you know, everybody has their own test suite. Everybody develops their own test suite in-house. This is natural. There are, of course, conformance test suites and those kinds of things that we can subject systems under test to, but both exist and both need to be plugged into a framework. We don't want to keep on rewriting that. We don't want to rewrite that every time somebody brings a device to powder. So we have this framework that's a workflow engine model. We have StackStorm up there, which is a common cloud integration workflow engine. It borrows a lot from its workflow model from Dataflow. You know, think of Dataflow workflow engines from the 90s and on. But it's specifically targeted to multi-cloud stack, multi-stack cases. So a workflow for us is to create a bunch of powder experiments, tie them all together with our flexible network infrastructure via our APIs, do some configuration management. We use Ansible a lot. We have a library of Ansible playbooks to do common tasks. We're adding to it as much as we can. Then trigger you know, some test suite execution and then persist the results in a test case management system. So every time we have a chance, we try to add some test workflows to the PlugFest use cases that we get. We've done this in combination with Keysight Technologies, who's been a great supporter of some of this and proving out some of the early automation. And here's one of our workflows for testing open source RICs with Keysight's RIC test. And the workflow is straightforward, as you might imagine. You stand up the system under test, stand up the test software, connect them, run the test, and then maybe you iterate over a parameter space. That's what my workflows do. You know, we developed the workflow first for the Open Networking Foundation's SDRAN RIC, and then we were trivially able to take the same workflow and just apply it to the OSC RIC. There's different, there are of course data that you want to gather from each RIC. RICs are not portable themselves. The ecosystem is not portable in that way. So there's some differences there of adaptation, but it was a big, this is just another way to look at how that fits into the ORAN ecosystem. This is the eventual picture that we want to drive to. The light blue boxes are just the disaggregated pieces of a 5G stack in a bracket, in a classic N10 bracket test setup. And what we'd like to get to is to have these workflows be very pluggable. So, now that we have our COTS ORUs that we're testing in the lab, my first mission when I get home, or my colleague's mission, is to plug srsRAN in there, make it work with our ORUs, and then have this as a library of building blocks in composable workflows that we can tie together and then give to the community and use as part of further OTIC testing efforts. And of course, the idea is that you can plug just about anything into those workflows. Thanks to the open interfaces, whether they're 3GPP or ORAN, both are important, but then you can rely on those things. Those who have stopped by Dustin's demo will recognize the figure down in the right. This is what Dustin is showing in the open source context, but this figure was done as part of some testing with Solona, a private 5G vendor. So we've been doing testing with Solona for quite some time. We started out in our controlled radio environment with a couple of their access points, and now we've moved those outdoors and collecting data and applying Dustin's log file gathering system to that to help understand what's going on and deliver that data for testing and analysis. So that's been fun. Another integration that we've done in the ORAN space using, or that we're trying to do, is with Mavenir, and this one requires a little bit more planning. These involve rooftop deployments and a little bit more infrastructure, and so this is in progress. I think we have the design all set to go. But then we'll stand up another version of this N10 test workflow using their equipment and make that available for their continuous testing. A lot of what we do is based around Keysight Technologies. They were an early supporter of this, and we're really thankful for that. So these are just examples of some of the other test workflows that we hope to implement eventually in our OTIC. Okay, that's all I've really got. That was very fast, but I hope it gave you a tour of what we're trying to accomplish, where we're going in the future. So please do feel free to contact us. Thank you.
Thanks very much, David. That was fantastic. I can see us booking flights to Salt Lake City sooner rather than later. Fantastic facilities. So I think we have time for 1 or 2 questions.
So this is a great presentation. A lot of things have happened since the time I visited a few years back. I have a question I also wanted to ask Elogio. Have you looked into integrating IMS type service into this end-to-end spectrum? We are just focusing on the core and RAN.
Not so much. Linking Reddit.
You can use this down with my question.
Thank you. That's a good question. And I think the answer is no, we haven't done that. We are really heavily focused on ORAN right now and spectrum sharing. Spectrum sharing that's the main problem we need to solve. That's where a lot of our energy is going. And now that we're actually starting to get some real ORUs, that's where our focus is. So, good question.
So you mentioned about the testing. What kind of automated testing you're doing? What kind of policy you are looking at?
As far as let me clarify, just as far as what kind of test suites basically are we supporting right now? Right, that's a harder question. So if you read the, and you probably have when you read the ORAN test specifications, those that exist, we've got 10 to 15 staffers. We've got a 600-page RU conformance test document to get through. That's impossible for us to implement, and that's where our collaborations with the test vendors really do come into play, is providing those test suites. We have some test suites. They're really oriented around basic 5G procedural testing and a little bit of performance testing. But so we're pushing both on that, is to develop our own, open source in-house kind of thing. But then we're also relying on the test vendors to really provide complete test coverage. I think, I heard comments about how open source test suites would be useful. They would be useful, but they are very expensive to develop and really prove out. That's my perspective anyway. Anybody else?
Thank you.
Okay, so with that, I think we'll thank our speaker.
Thank you very much.